Franco-Italian. Sorry, is a Brazilian-Italian, right?
Yeah.
So she's a perfect Portuguese speaker. So questions could be in Portuguese and English and Italian, right? Camilla did a bachelor in astronomy in Padova. After that, she moved to the College London, where she did the PhD and the master, right? So she studied the atmospheres. And now she do these excellent works in planets, detection, and all this that she showed today. So Camille, it's a pleasure to be here with you. And
thank you very much, Jose. And thank you for all of the organizers. It's, maybe you're not aware, but this kind of program is it's absolutely new. It's like I've never seen in my career someone putting together in a school such a large topic, going from large-scale structure down to exoplanet. So I think you should feel privileged, like, to be here and like participating in this synergy program, because it's very exciting. So before starting and going to science, I just wanted to give you an overview of my career, because I always believe that being like students, you wonder how is the future, and you wonder like what you will have to do to get a permanent position and find your field, the thing that you like. So I just wanted to give an overview of what I did. I had my bachelor astronomy, so in Italy it's 3 years, in Padova. Then I saw a public lecture on atmosphere of exoplanets, and so I decided I wanted to move to London, because London was the place to do atmosphere of exoplanets. I went there, I did my master, it was 1 year, and then I did my PhD, that is 3 years, in Europe usually it's 3 years, on the optimal extraction of planetary signal out of instrumental and astrophysical noise. After that, I applied for a job in Paris, and so I moved to Paris to the IAS, which is, well, the first institute there. And after the IAS, I started working on different topics, and then I did a second fellowship in the Observatoire de Paris, which was covered by the Space Agency of France, the CNES. And then I did like another postdoc at the CEA, working on JWST simulations. So for a total of 7 years. After these 7 years, luckily always in the same city, so I just changed the institute, that was nice. I moved to Spain, where I did 3 years postdoc. And after that, I got a fellowship in Italy for 3 years in Arcetri, the Observatory of Arcetri. And next year, I will move back to the University of Valencia, where I got a permanent position there, a tenure track. And specifically, I will work on detecting exoplanets with gravitational waves. But exactly, like, research sometimes is not that fluid, right? You might have to learn new things and like expect the unexpected. So I really want to do atmosphere of exoplanets. But then in the end, I decided that like I need to do some stellar activity trending, because to study the atmosphere of the exoplanet, you really need to know the stars. You really need to understand if what you're seeing is the stellar noise or it's actually the atmosphere of the exoplanet. So I did some stellar activity in the trending. And then I moved to direct imaging of exoplanets. So I prepared a simulation for JWST, what we were about to see with the MIRI instruments. So this is the famous system with 4 planets, HRA 8799. And then I worked for determining the Gaia extinction coefficient in the Gaia consortium. I'm currently the stellar characterization coordinator of the I'm the coordinator of the Stellar Characterization Working Group of the Ariel space mission, which is a mission dedicated for the study of atmosphere of exoplanets. That is going to be launched in 2029, after Plato. And I'm coordinating the interdisciplinary working group for the LISA mission for developing the science case on the detection of planets with gravitational waves. It's highly interdisciplinary, because you might need to think like you have gravitational wave experts, you have double wide dwarfs experts, you have planetary experts, planetary formation experts. It's a very interesting work. So as you see, it's like stuff can happen. You just need to be flexible and adapt yourself. And every skill that you learn in one postdoc, it can be applied absolutely to the other postdoc, even if the subject is different. Okay, so, And last thing, I was born as an observer, because I really like to do observation. That was like photos I took in the observatory in South Africa. So this is SALT, it's a 10 meters telescope in the southern hemisphere. That was the control room of the 1 meter dome, where I was observing this exoplanet observation of microlensing. And that was like the night sky picture that I took. That was the dome I was working in. So this observation resulted like as being part of a publication that a couple of publications that we published. Again, I was born as observer, but like life is unexpected. So at the moment, I'm basically doing theory. So also that can change, you know. Right. So this is of the view for the course. Of the things I would like to talk about. We'll start with today with the stellar binary evolution. Then we'll go on the long-term evolution of planetary system. The third one will be detecting exoplanetary gravitational wave. And the fourth one will be mostly about the disk that can appear after the post-HGB phase and the fact that you can have planets that are born even there. Okay, let's go with stellar evolution. It's going to be a quick overview on stellar evolution, but you already did that with Sydney, I think. And I will focus mostly on the closed binary evolution. Okay, so how many of you know like what is the HR diagram? You just need to raise your hand. Okay, great. So for the others, the HR diagram is basically a way to characterize and classify the stars. We have the brightness in here, and then we have the temperature in here. This is the main sequence, so where the stars spend most of the time. And then, depending by their temperature and then brightness, we classify the stars in spectral types, right? So observing them through a spectra, you might see different kind of lines, and depending by the lines that they have of elements, of course, I'm talking about like molecular elemental lines, you have a spectral type. So it's the system is called Morgan-Keenan system, and it's called all of the stars. Well, it's a weird, like, someone would think that it would be like alphabetical order, but no. The way to remind that is always, oh, be a fine girl, kiss me, right? So, oh, be a fine girl, kiss me. So very hot, very massive, very cold, and very small, and very tiny, tiny, right? Okay. So again, like the brightness is measured like the absolute magnitude as a function of the temperature, and then you have here you don't see it, but you have a line of constant radius. So when a star is formed, then it can evolve, and then, for example, here you see that you have the giant stars, but then also in stellar evolution you will have also the white dwarf stars. And now we are going to go more into detail. So these are very old. And these are old stars. These are funky stars. And then, yeah. Yeah, and that's everything I want to show you in here. So again, I'm pretty sure that Sydney already talked about it, like about the formation of a star. So star formation happens inside the molecular cloud in interstellar space, and basically these star-forming regions are also called stellar nursery, and they are usually found inside a nebula. A nebula is made out of dust, hydrogen, helium, and other ionized gas. And funny fact, indeed, I like to put it there, a nebula the size of Earth would have a total mass of a few kilograms. That give you more or less an idea of the density and what we are talking about. And this is one of the photos that was taken by JWST, where you actually see the clear differences between the nebula and the star-forming region. Well, you have star-forming region. Okay, so again, as I am an observer, I'm going to come here because otherwise I don't see. So this is the whole process, and we are going to go through that. But like, I like you to see the observation that were taken with ALMA. So you have ALMA, that it was like the blue contour. And then you have the VLA, which is the very large array. Those are interferometric observations. And automatically, they are taking the picture of that phase of stellar formation. So you have, we have a dense clump of molecular cloud that it collapses in the center. And then a region, opaque region, starts forming in the middle. Then you will have an hydrostatic core, which is basically a core in hydrostatic equilibrium, like Ramil said before. That is like creating due to an increase of pressure and temperature. But because of the angular momentum, a disk is going to start like forming around it. And then you will have, again, like infalling material in it. So you see that there is that's the clump, and then you see that there is some infalling materials. This is obviously like an artistic expression, right? But this is the data. And then you have that the central region is denser and forms into a protostar. Then you start having like some outflows. So outflows are basically stellar wind. And then you have that, it might be that in the outer case, the disk is forming a planetary system. But obviously, it depends by the different condition. And then we have the last step where infall stops when the protostar begins the thermonuclear fusion and produce outflows that break through the envelope. And those, we can see it in the visible. When we say like it's optically visible, you mean that you see it in the visible band, not it's just in that sense, not that we can see by eye. So a typical class 0 protostar without flows, as it's actively accreting, and it has a supported disk rotating around. Okay, so let's put star formation in the context of the HR diagram, where it happens. Well, it happens before we enter the main sequence. So this is, again, the HR diagram, temperature, the function of the luminosity. But you have your star that is forming here, protostar that is forming here. And so it's forming, and then step 2, we have the protostar that shrinks and heats as the gravitational potential and energy is converted into thermal energy. So it's gonna shrink down. But by shrinking down, like you have the surface temperature rises. And then in the end, like you have the diffusion rate increases until the balance the energy radiated from the stellar surface. And in that moment, you are inside the main sequence. So from the outside, you're just coming inside for the formation process of the star. And then the main sequence is where the star is going to spend most of the time. But again, like it depends by the function, the initial mass that you have of your protocloud, right? So here you have all of the tracks, the black ones, as a function of the stellar mass. So you see, like the sun is going to go did this track and enter inside the main sequence. But then, like a 15 solar mass is going to do another different track. So it's a different kind of evolution depending on the initial mass you have. Always need to think that star formation and stellar evolution, it depends by the mass you are dealing with. Okie dokie. Indeed, how long does a single, I always put single because I like more binaries, but yeah. How long does a single star survive? You have here like a very nice picture of, as a function of your mass and a function of time, what is going to happen to different class of stars. So you might have, again, like a protostar for the sun, a solar-like star is going to go giant, and then you're going to have the planetary nebula, and then a beautiful white dwarf. But then the case is different from a very massive star where it goes blue supergiant and then already explodes because it's just too much mass and it's going to just collapse, you know, and then it's going to explode. So the more massive, the faster it burns out the fuel, and then the faster it's going to die. Yeah, okay, this is actually like the most massive is going to go supernova. But the lowest one, so this tiny thingy, basically they're never going to evolve, not the brown dwarfs, just the other one, the M dwarfs. Some of them, they're never going to evolve before the end of the universe, right? So 1/10 of the mass of the sun, this tiny one, and can burn hydrogen to up to 1 trillion years. So the current age of the universe is 13.8, 10 to the billion years. And then that will be how long this star is going to survive, the one with low mass. OK, so again, this is just to strengthen the fact that as a function of the initial mass, you have a different kind of evolution. So that's the one I told you about. That's the, well, small star can be also sun, ideally. So you get to the white dwarf. But then in the case of more massive one, you might have like a very strong explosion. So you have a large star, then you go for a red supergiant. And in that case, like a supernova can be triggered, basically, by the collapse of the own star, and can be triggered by the reignition of nuclear fusion of the degenerate star, or as well by the gravitational collapse of the core of a massive star. And in that case, it can, it can become like either a neutron star or a black hole. The difference between those is depending basically by the mass. So when the mass is larger, the gravity will be that strong that like the neutron star can just collapse and shrink into a black hole. Up till here, any questions? So what's the typical thing, the typical variable that we need to take into account for stellar evolution? It's the? Yeah, great. So yeah, you can have mellow explosions, strong explosion, and catastrophic explosion. It's basically Game of Thrones over and over, like you have chaos and explosion and blood, no, but a lot of hydrogen that's coming out. Okay. But what is life after the main sequence? Right, again, as a function, yeah, as a function of the mass, a star enters the main sequence, stays into the main sequence, at some point it needs to evolve. But again, like it's a function of the mass. So you're going to have different tracks to come out and different phases, like going through red giant, not going through red giant, exploding, always as a function of the mass. This is basically a representation in the HR diagram of this. Okay? So this is for all of the stars. I always liked this plot, so I wanted to put it. This is related to the sun, exactly what is going to happen to our sun. So we are here in the ZAMS, so you're going to have like the evolution through here. We goes through a horizontal branch. It's going to have the helium fresh, and then it's going to end the helium fusion, and then it's going to go up again in asymptotic branch, and then carbon core growing, and then we'll start like having the post-RGB phase, and have planetary nebula formation in here, and then it's gonna go, bam, down to the white dwarf branch. Basically, you have the core of the star, of the sun, that is gonna have a very high temperature, and then it's gonna cool down and do this, as you can see here. Indeed, that's worth for everyone, it's still the sun. You have the post-RGB phase, and then it's going to go in the white dwarfs region, where they are. It can be hot stars, and it can be also very, very cold stars, but very, very tiny. More on this later. And then I put pretty pictures of the planetary nebula stage. So these are really taken. Then here you can see, indeed, the white dwarf. So initially it was called planetary picture because you thought that it was caused by the presence of planets. So it's not because it's related to planets. It's just evolution, it's a historical name, and that's why we call it planetary nebula, not because of a planet. Okay. So a while ago, Gaia was launched. Gaia was a survey to study all of the stars, all of the sky, and it gave us so much groundbreaking discoveries. And you see here all of the stars that it detected. So you have the main sequence, the giant branch. Now you can see also, not in this one, but the horizontal branch that, like, with increasing the sample is going to help you to define the HR diagram. And then the thing I love the most, it was indeed the white dwarfs population. We really didn't know many white dwarfs because they are faint, but then with Gaia, just checking the parallax and doing it through astronomy, we could detect so many white dwarfs. And this is mind-blowing because they started seeing, scientists, that we have two different populations in here. Now it's more defined, but in here you have this one that is going up, But then there's a secondary one that is going down. Kind of you see like a hole in the middle. And you're trying to understand why this is happening. And so this is obviously like an internal structure of the star. It can be due to crystallization and other aspects. But that's the beauty of like observation. You have a telescope out there that is collecting so much data that you can start doing a population, a demographic of the things that you're seeing. Okay, but what is indeed a white dwarf? So it's a dead core, as I said. After it explodes, you have the dead core inside. We call it dead star, but they're not really dead, unless you want to call them zombie. But they have a mass of similar to the sun, and then the size of Earth. So it's a very compact object. Usually, it's basically having a teaspoon of sugar that is like weighting, like it has the weight of an elephant. That's exactly a white dwarf, right? Okay, so the centripetal gravitational force is balanced by the external quantum pressure. They can go supernova. They can be very, very hot. So, oh, sorry, that was the gravity. I'm sorry, but they can be very, very hot. We're talking about like 30,000 Kelvin and so on. So it really spans the whole range of temperature when it's cooling down. It's a dead star in the sense that it's cooling down. It starts very hot and then it cools down and it goes black dwarf, because that's the very, very end. After the white dwarf, it stops radiating any energy it has inside, and it goes black. So we call it black dwarfs. 90% of the stars in the Milky Way will become white dwarfs, and almost all white dwarfs have the peak of the mass is 0.6 solar masses. And they have atmospheres. It can be hydrogen atmospheres, or helium atmosphere, or carbon-oxygen atmospheres, or sometimes a combination. Okay, another good characteristic of these stars is that's the Sirius B, by the way. It's a real comparison with the star. Sirius B is a white dwarf. They cannot have masses larger than 1.4. So Chandrasekhar got his Nobel Prize in 1993 to find out that the electrodegeneracy pressure could not support a force of gravity that was corresponding to more than 1.4 solar masses. So anything above that, we would have a collapse of the star, becoming maybe either a neutron star or a supernova. Or, no, sorry, a black hole, yeah. Right, and now we go to compact binary evolution. Okay, so what is a binary? Do you want to answer that? Okay, fine. It's so difficult, right? So a binary is like two bodies, one like rotating each other like around the center of mass. Pair of stars in that case, because you can have binary of different kind. Alessandro likes binary of black holes. I like binary of white dwarfs. They can be visible by direct imaging, spectroscopy. By basically observing the spectra of the star, you see the lines that are periodically shifting. And then also through photometry. And they're very important to measure the masses of stars. You have different architecture, of course. So ideally, like from a nebula, you can find... Okay, now, first of all, half of the population in the Milky Way is in binary or higher multiples. So we're talking about a large fraction of the stars in the Milky Way. So you might have a single, a normal binary configuration, which is the first one, or you might have like other kind of configuration. And most of them are in hierarchical system, which basically means that you have an inner binary and then a third body outside. But basically, given that they are so far away, you can consider them as a binary itself. So the inner one will be one single body, and then the outer body, and then they are in binary. So that's the definition of a hierarchical system. So they can. If we talk just about the first case, the A case, if the stars, the binary, are very far away, we call them wide binaries. But if they are close to each other, we call them compact binary or close binary. And usually this is the range of less than 10 astronomical units. Those are the compact ones. Yeah, there's nothing very interesting about the wide binaries because they just evolve. Like the most massive one is going to evolve first, and that's okay. They're far away, and then the second one is going to evolve, and that's fine. And boring. So, yeah. Yeah. No, exactly. Like for me, they are extremely boring because there's nothing happening. But I can see why for him, like they're very interesting. Because working in different fields, when I was doing atmospheres, I always had stellar scientists coming up to me saying like, okay, so your noise is my signal. Can we do a collaboration? So maybe you can give me your noise and analyze your noise being my signal. So for different kind of research you might have, that for someone is boring, for someone is interesting, and yeah, okay. Right, let's carry on. While exactly in the other case they interact, but more on that later. Okay, so when you have a binary system, you have a region of space that is controlled gravitationally, and so you will have the definition of the Roche lobe, where we have, depending by the size of the star, you might have a larger. The more massive your star, the larger your Roche lobe, and the smaller the Roche lobe, right? Is proportional to the mass of the star. So these are two stars. This is obviously hotter, so more massive, and it's going to have the larger Roche lobe. And both of the Roche lobe, they meet in the Lagrangian point. So the definition of the Roche lobe was basically it's an equivalent radius of a sphere that has this volume. And it was found that this is the simple formulation, but it was found with numerical integration of the gravitational potential. Just a point on the Lagrangian point is basically when you have the same attraction and repulsion. So it would be in here. You have other Lagrangian point. This is the L one, but in a case of a binary, you have like other Lagrangian point, and usually those are where we send satellites because they are the places where they are more stable gravitationally, and they will move with the whole system. They will not just go everywhere. You might have more stable Lagrangian point and less stable Lagrangian point. Okay, so let's go to the exciting thing. They interact extensively with the separation of less than AU. What I like is that when one is becoming larger, obviously the atmosphere is not just going to stay, of that star is not just going to stay with that star, but it's going to interact with the second star. And it can affect the evolution of both of the stars because basically they shared an atmosphere at some point in the evolution. There are two important steps in the evolution of a closed binary. When the most massive star is going to become a giant, and when the second star is going to become a giant. Why is that? Okay, so again, we have star 1, star 2, and then our Roche lobes, and then at some point, the first one is going to go red giant, and it's going to fill the Roche lobe. When it fills the Roche lobe, two things can happen. You might have a stable mass transfer, or you might have an unstable mass transfer. The stable mass transfer is stable. So it's a slow one. It's gonna just start giving material to the star, and the star is gonna grow compared to here. It's gonna grow in a stable way. So again, nothing very chaotic happens here. It happens when you have an unstable mass transfer, such as in here, where you have a mass transfer stream, and then it's chaotic, and then what happens is basically a common envelope happens. As I said, the first star is going to share its atmosphere with the second star, and then we call it common envelope. So this is at the beginning of the common envelope, but it's going to go through the Lagrangian point and pass all of the masses, transferring all the gas to another companion, but it's doing like in a very violent way that this star here is not going to accept it that easily, right? So what is very interesting here that we're talking about what is the biggest unknown in stellar physics. There are so many things happening with this mass transfer, and there are so many variables that we're going to go through that it's one of the things that we still don't know, that there are a lot of modeling going on, but like the number of double white dwarfs that we detected are very few, so it's very difficult to trace down. But again, there's some progress. So this is an overview of what is happening. We start from an initial star, and then we have Roche-Lobe overflow, that is like passing the material. You might have the stable case, or you might have the unstable case. In the unstable case, you can go to a common envelope phase. And when you are in the common envelope phase, two things can happen. The coolest one is the envelope ejection, and then you will have a white dwarf and another main sequence stars, or you can merge in one single star, okay? Okay, but let's carry on from here. Then we have white dwarf and main sequence star. You might have, again, another Roche-Lobe overflow, right? So this one is going to pass material to the white dwarf. And then, again, you can be stable or unstable, a second common envelope. But then here, you can go either to merger, or you can have a Roche-Lobe overflow, and then have an H-rich donor. Or then you can have another ejection, and then a formation of a double white dwarf, which, of course, is going to rotate, like orbit each other until they're going to merge. But you see, it's like, you know, those kind of like books where you just go through the end of the chapter, and then it says, like, OK, you decide now. And then if you decide this, you're going to go to that chapter. If you decide this, you're going to go to the other chapter. It's exactly the same thing. Many things can happen. You can have also a stable mass transfer, and other things can happen. So it's a very complicated problem. But again, if I just observe that, can any one of you tell me what was the progenitor? So what was, which kind of stars we had at the beginning? And then I have like, no, because you saw that it's very complicated, like to trace it back, right? So wait, no, I really like that. So I'm just gonna put that. So that's my face every single time, you know? Okay, but again, so I just put this back here to give you more idea what you can form. You might have double degenerate, so you might have two white dwarfs of CO atmosphere, or can be CO and helium atmosphere. You can have a single white dwarf because it's merging. You can have a supernova one type, or you can also have other H-donor system and then other supernova. So depending really by the type of evolution, you have a different outcome. So what do you think we need to take into account when evolving a binary system? OK, so we have a stellar evolution. So obviously, each star is going to go through their single evolution. Other things, it's a binary. So what else do we have to account for? What? Well, it's basically it's the dynamic, right? So we have stellar dynamics. So it's after that, yes. You have a two-body system for which you have to check whether the mass transfer is stable, the mass transfer is how it is in general. But after that, you also have to know about like the kind of mass loss on one side and the kind of accretion on the other side. And then you have obviously losing mass. You have like an angular momentum loss. And then you can have also the production of gravitational waves. You can have magnetic braking, and you can have tidal effects. So just imagine putting all of these ingredients inside into a simulation. Yay. OK. We can do that. There are codes that do that. So it's called the binary population synthesis. So the goal is to do a simulation, to then trying to match it to the observation and trying to understand if what your ingredient that you're putting in, they're actually working. So Binary population synthesis, theoretical modeling of stellar and binary evolution. Well, there are different codes. Usually, you put inside an n-body code, recipe for stellar and binary evolution. But then you do also, you have some priors, such as the initial distribution of the mass ratio, the separation, and the eccentricity. You also need to account for the stellar formation history, so in the galaxy, and the link of the observation. So this is one simulation that was done with the SEBA code. It's a courtesy of one colleague of mine, which is Sylvia Tonen. So you have different parameter space. This is the separation of the binary and then the mass. And depending by where they are, you have a stable mass transfer, you have the common envelope, and then you have no interaction at all. Okay? So this is before the progenitors of what will be a white dwarf plus a main sequence star. And then you make it evolve through the code, and this is the result. But again, check at the y-axis. So here you go up to 10 solar masses, but then what your result is going to be up to 1.4. It's just to make you do a comparison yourself, right? So this is, again, the no interaction ones, and then what went through the stable system, and then the common envelope phase. So it's just a comparison of the same parameters before and after, depending by the type of evolution they had. As I mentioned, there are different codes that are doing that. In particular, you have binary C, SEBA, which is the previous slide, and Star Trek. Funky names. And again, you have here the different groups of evolution: common envelope, stable mass transfer, and no interaction. Most of them, you can see that they are quite similar, but at the naked eye. But obviously, there are some differences that usually are based between tiny factors that are different between the code, one code or the other, or the type of the evolution for the single star. Okay, so obviously you might have uncertainties in your binary population code. It can be given by just a single star evolution, or also on the dynamics, which of course, like the biggest one is the common envelope evolution. You know when and what is the outcome, when it happens, and which kind of common envelope you might have. And then yeah, it's always, like, as I already mentioned before, the stability of the mass transfer, it's kind of tricky. So thing is, like, when the star loses mass, the Roche lobe automatically would shrink down. So you need to account for that and like automatically change it in the evolution itself to account for the shrinking and the shrinking of the orbit. So it's yeah. Okay. Right. So the most famous way to approach the common envelope is through phase. It's through the alpha CA formalism, for which you have here an example of the mass ratio and the time of the evolution. So in mega year, 0, 800, and so on. And then the variation of the separation, right? So you see well, the variation of the separation, the first common envelope and then the second envelope, common envelope. This kind of formalism is based on energy balance, which means basically that you are the change of in the orbital energy of the system is used to provide the energy required to unbind the envelope. So basically, you do the difference in binding. Like the energy for unbinding the envelope. The difference is equal to the difference of the orbital energy. With the factor alpha, and that's the formula that you use to account for that. But yet again, this was the most used formalism. The problem is that you see that the models are the gray dots, and the blue points are the observations. So you have the mass ratio of massive over smallest star as a function of the separation. And then you see that you can indeed see larger mass ratio observed. So the model is not working well. What's happening? Obviously, there's something we're not accounting for. So there was a second formalism that was introduced by Nellemans in 2000, and it's the gamma formalism, which is based on the angular momentum balance. So the mass loss of the star reduces the angular momentum of the system according to this formula. And this is for explaining the fact that in the first common envelope, the stars are not going to get so close. They're going to stay like still separated. But this is going to be maybe more clear for you. Alpha case and gamma case. So this is the same system, right? So it's happening like the first common envelope for both is happening 800 mega years. They have a separation of 508. But in the first case, after the first common envelope, they have a separation on 38 solar radii, while here is 375. So you see that it's like there's a huge difference between the two formalism. So current models are saying that, well, no, let's carry on with this. And this is the difference again. You see that at least in here, in this case, you are matching a bit more the model, the gray dots are matching a bit more the observations. But this is, yeah. This is still not the final answer, because ideally now they're thinking that in the first common envelope you have a gamma formalism, and in the second common envelope you have an alpha formalism, so a combination of the two. So you really need to constantly update your models based on your observation. And one important thing when we are talking about binary is indeed the binary mass the mass ratio, because it gives us an information of the kind of evolution depending by where they were, how it happens. So if in the first common envelope the orbit shrinks a lot, when the secondary star is going to feel its Rho slope, it's going to be less evolved, because obviously it's going to feel the Rho slope much more quicker than being far away, you know? And then the core will be smaller, so you will have a difference in the mass ratio which is much larger than if they were to evolve a bit further away. So by observing the mass ratio between the double white dwarfs in the end, we have an idea of how their orbit stays and how it evolves in terms of separation. Also, again, because it's not matching perfectly, they're still thinking that there are more stable mass transfer. Up till now, the idea was most of the time it was happening a common envelope phase, it's just on a stable mass transfer. But in the recent development, after all of the new detection that they had, there's this idea that the stable mass transfer cases are larger. Okay, so we are almost towards the end. So I wanted to give you some numbers, because we keep thinking about white dwarfs and double white dwarfs, but you know they have their time of evolution, and the universe has its own age. So if we just look at the double white dwarf space density, we have the frequency is 4.8 10 to the minus 3 per parsec to the minus 3. So it's very little. And also the synthetic population is more or less matching this number. But then when we talk about the space density of the double white dwarf, as in the number of double white dwarfs as a frequency factor compared to the number of white dwarfs, you have that this is very different depending by the person. Well, it's very different, okay? I mean, to you it might not look like that different, but it can give you a different kind of population in the end, of course. So depending by the work that we're doing, like indeed, if you just have a look at the at the time of the publication. That is the interesting thing, like how the frequency can change at the time of the publication, depending by the detection that you had with new instruments, new technology came up. Oh, wow, look, another system there, another system there. Oh, I'm increasing my sample. Oh, then like I can run new simulation. Okay, let's match it again. Like, oh, like the frequency is higher, the frequency is lower, and so on. So you keep adjusting it because it's not just a matter of like doing theory and doing observation. The real game is like putting everything together. And then again, if you do a synthetic simulation, you might have the frequency for the alpha formalism and the frequency for the gamma formalism. Right. Yeah. So when you observe, how do I explain that? No, you need to know that your sample, the things that you're observing is complete. You need to know that the area that you observed is really, you observe it very well, and those are the numbers of stars that are in there. Like, then we call it that the survey is complete. So we have a complete survey of white dwarfs within 20 parsec from Earth. Okay, 20 parsec is very close. But then we are sure about the numbers we found. So it's 95.96 plus minus 3 white dwarfs, and then 2.1 wide white dwarfs, and then you might have 1 compact white dwarf, double white dwarfs, and possibly 4 candidates, right? If you go further out, obviously it's going to be more difficult to have a complete survey, because like you need to make sure that indeed you accounted like for any tiny angular space in the sky to check that you don't have that kind of target, right? So for the predicted Gaia sample, it's 50 parsec, and then you might have indeed an increase of single white dwarf and compact white dwarf, double white dwarf, sorry, for less than 4 double-degenerate progenitors, and double-degenerate might be also a combination of neutron star with a white dwarf, or it can be 2 neutron stars and so on. But why do we have such an increase? Like we go from 95 to 1400 and 1900. Well, you have different aspects, right? One is that you have different kind of observations, because Gaia is going to observe through parallaxes, so astrometry, and that will help to go a bit farther out, because you the limited magnitude of observation of Gaia goes much more fainter, so it can go further out in space to sound other systems. And also because, well, I mean, like closer to us is less populated, right? The further you go outside, it's more populated on a different scales, of course. I'm not saying that in 50 is more populated, but this is the factor. If you go towards the center of the galaxy, of course, you're going to have many, many more stars and many more double white dwarfs. Okay, so I actually finished a bit earlier. This is I just wanted to give you an overview of closed binary evolution. I will explain why we can use them to detect exoplanets in another lecture. So I just wanted to leave you this, like, you have a double white dwarf that is formed today, but then the orbit is going to start shrinking, and then at some point it's going to just merge. And when it merges, if the mass is like more than 1.4, you're going to have a supernova 1 type, or you might have formation, the merge, yeah, the super, yeah, no, okay. If it's more than that, yes, or a black hole, tiny black hole, or otherwise you can just merge and become one white dwarf. Yeah, and that's it. Any questions?
Please, questions, comments? This one.
Thanks for the lecture. I got a little confused by the different mass transfer regimes. So, like, there is no. Is there like a is slow mass transfer and common envelope phases, are they like completely different things, or can they like happen together?
No, they cannot happen together. Basically, the difference that one happens in a violent way, and so you can also call it like a rapid mass transfer, fast mass transfer, and the other is like a more slow. So the second star has time to adjust and accrete, and yeah.
And well, you have and so you have these two steps where each companion goes unstable. And like, does the first step influence the other?
Yes. Yes. So, for instance, like here, let's assume that you have, let's say like this is an M dwarf, right? If you go in the stable mass, you might have that this is just going to accrete material and just change its nature. It's not going to be anymore a white dwarf, sorry, a brown, an M dwarf, but it's going to be, I don't know, an F type. So it's going to change its internal structure, and then its consequent evolution will be as a function of the new type of star that became. In here, it will stay an M dwarf, but it's just gonna like, it doesn't have time to adjust like the internal processes in the star, and it's just gonna, you're just gonna have a peanut shape, you know, where everything, you have the two cores of the stars inside a whole global atmosphere. So obviously, it's going to affect the second one. So because if this happens very fast, this is, well, sorry, the second star is going to behave differently. So that's the famous black box of this type of evolution, close evolution.
Another question?
Hi, thank you for the lecture. I wonder, when you talk about the number of binaries on 10 parsec like radius. So maybe I missed something, but you have like a statistic of I think it was before the last slide, the one before.
So my computer is slow. This one?
Yeah, maybe, yeah. So you have like a non-integer numbers on the population of white dwarf, and why is that?
It's given by a probability.
So it took maybe a limit to continuous. You have like a discrete distribution, and maybe you.
Just give me a second. So you basically have all of the observation. What did you say? Sorry.
No. Maybe I was thinking that maybe you have a discrete distribution of the number of white dwarfs. But maybe you take a limit to the continuous. I don't know.
We can check afterwards, because I don't really remember that, like how they do it. Usually, it's a number that is inferred after different surveys, and then you do a probability estimate of what it will have to be in 20 parsec due to the population that you're expecting within 20 parsec and so on.
Okay, thanks.
Another one. left side. Only left today, right? Good.
Thank you for your lecture. One question. One main ingredient is the moment lost. And in a compact white dwarf binary, the only way to lost moment is through the gravitational waves, right?
Yes. Oh, yes. No. No, also with the mass transfer as well.
Oh,
but what you're saying after, when it's formed, yes.
Yes.
Yeah. After it's formed, yes.
A compact white dwarf binary.
Yeah. So basically, the orbit is just shrinking because it's releasing gravitational waves.
Okay. And how you can differentiate between the action of alpha and gamma process is through the binary separation?
Both binary separation. Well, it's this, right? So both binary separation and the mass ratio of the stars that you're observing. So it's both of the combination, because the binary separation, you would expect it to have, if you go just with one formalism, you would expect it to have a specific mass ratio. But when it doesn't, it means that there's something that is not correct. So you try to compensate that. And okay, so that was before the alpha, and then they invented, they formulated the gamma. But now in the code that is matching the most the observation, which is SIBA, they use gamma formalism for the first common envelope, and then alpha formalism for the second common envelope. So it's a mix of the two. Because both of them are, I mean, they're valid. And it's not that one is wrong as the other is not wrong. It's just that you need to understand, like, it's a mix of the two. But the main thing is, like, you really need to go and check your output of your simulations and the observation that we are seeing, like the data that we have.
Thank you.
You're welcome.
Another question, maybe from this side now.
This side is cosmology.
Yes, it's divided by two samples. So two guys, girls now, probably.
So who's actually like galaxy?
I think it's more
extragalactic. Who of you of astronomers is extragalactic? You can raise your hand. Well, I don't see otherwise.
Shy.
1, 2, 3, 4, 5, 6. Who is galactic? 7 here. 1, 2. So galactic means basically Milky Way. So star formation in the Milky Way, planets, stars, and asteroids.
Yeah.
Those who didn't raise and in either are gravitational wave astronomer, maybe.
Yeah,
Okay,
true.
yeah.
Like, okay, fine.
Those
And the physicists, who are the gravitational waves astronomer then? 1, 2, 3, 4. Oh, that's why you said the covalent before you said. That's not a word we used in astrophysics. I was like, what? Okay.
Questions again? So I have one comment. Okay, Camilla.
Yeah. Oh.
As another Camilo, have
Right.
two Camillas in the room, right?
Yeah. Okay, thanks you for the lectures. And I think that you will talking about in another lecture, but what would the formation of planets in this binary system look like? I mean,
in which moment? After they became double white dwarf or before? Because, okay, I'm gonna quickly answer that. So if you have a planetary system that is forming around a binary, it's, well, we'll go through that, but it's basically the same kind of formation you have that Vladimir explained last week. Because you have, It's the same. It's just a different configuration, and you might have, you do have a region of, very specific region of where the system will have to be stable or not, but that's fine. Now just think about that. So you have two stars that are evolving. Automatically, they are changing, like during the evolution, they are changing the chemistry inside. And then in the case of a compact binary, you might have that after a common envelope, you have the ejection of the common envelope, but it's proven, theory, that like 10% of this mass is not gonna reach the escape velocity. So it's gonna stay attached to the disk, to the binary, and it's gonna form, for angular momentum, it's gonna form a disk. Yet this disk is chemistry is very different from the previous one, because it's gonna be more metal. So in the case you have more metals, you have the opportunity to grow much easier a giant planet, for example. But also is around a star that is like 30,000 Kelvin, right? So it's very hot. By being very hot, you have a lot of like radiation over it. So the disk is also going to evaporate quicker than in the previous case. So the type of formation can be the same. But what it changes really is the environment of the formation, the kind of disk that you have, the size of the disk, and also the fact that you're dealing with a very hot star that is like messing up quite a few things.
Okay, thank you.
You're welcome.
Good. Other questions? Decide? No? Well, a comment about the Bernard question, right? You asked about what's happening when the binary stars transfer mass, and the evolution, I mean, is different, right? So the physical fundamental problem is about the mass affect the transfer situation, the other star. So the pressure is too much. So the evolution is affected by that. So these small stars evolve too fast, and the other one, less massive now, evolve in different ways. So it's completely different from a single one system. So that is the fundamental difference, yeah. And I have a question for you. It's this Gaia diagram that you showed, this white dwarf.
That was the
diagram.
DR1 still.
It's amazing, yeah.
I think that now with the DR3, I couldn't find it online, a pretty one, because I wanted a pretty one.
Yeah. It's amazing. I mean, this population
it's
below, yeah, that.
Yeah, I know.
One.
This one.
So now I have, I mean, there's more exotic planets is around the white dwarf, right? So we have 2 or 3, it's not too much. So we have exoplanets in this part of the Arcetri diagram. Mm. So what to think about that? It's a good topic to the future?
It's a gold mine.
Okay, you answer.
No, having a planet around a white dwarf is very interesting because you see in the future, right? It's a planet that survived the evolution of the stars. So studying those kind of planets, planetary systems, sorry, not planets, you have an idea whether as a solar system, we can survive when the sun is gonna evolve. And it gives us so much information on indeed the final fate of planetary system. So most of the people are now focused on main sequence stars with planets, and they're starting like to have some interest around the white dwarfs, but it's difficult to find them because the stars are faint. So you find them through microlensing, you find them through, well, I'll tell about the methods tomorrow. Microlensing, you find them through transit. It's very difficult to find through radial velocity because you have to observe the star and what? Okay. When you do radial velocity, you basically pin down the lines of a spectrum of a star, and you check them if it's changing and it's shifting. But these stars are faint, and they are not very well known to have lines. You might have one hydrogen line, and that's it. So you cannot really do anything precision in that case. Yet, you've seen the photo of like Sirius and the Earth. They are exactly the same size. So just try to imagine a giant planet that is like passing in front of a white dwarf. It's just going to kill the light of the white dwarf directly. So in that sense, it's easier. But depending by the methods, it might be more easier or less easier. But tomorrow we'll talk a bit more about that, yeah.
Another? We have time, probably. Well, another kind of system that is very interesting is binaries with a planet that go far. I mean, it's a circulate planet in these two binaries, right? It's not. Could you comment about these planets? I mean, circle-binary planets, yeah.
Yeah, tomorrow, a whole lecture. They exist, but it's very difficult to find them as well, again. We know 15 of them at the moment. Okay, over 5,700 exoplanets have been discovered, by the way.
This is Star Wars planets, right? In the Star Wars movie, we have this planet with two suns in the sky.
No, that's, so. Yeah, that's Tatooine. Yes, yeah. That's Star Wars. I never watched Star Wars, I'm sorry. I'm a terrible person, I know.
Okay. Tatooine planet. No more? So, thanks again, Camilla.
You're welcome.